Okay, so I'm Adam, founder of SkyMind. So just a little bit about me. So SkyMind is basically open source support services and training around a distributed deep learning framework. So one of the questions my customers ask me often is, how long do your neural nets take to train? And why should I use you over the number of open source solutions that are already out there? In this case, one of the problems with deep learning is most companies have the data, they have the infrastructure, but they don't want to write their own deep learning algorithms. But they're stuck with these solutions where they don't get support for them, and most of all, they don't necessarily know how to tune them. And on top of that, you know, like at Alibaba or any of these other research groups I've talked to, many of these neural nets take days to train. So one of the problems with deep learning is, yeah, I'm saying problems, yes, even though I'm doing deep learning myself. One of the problems that makes it intractable is being able to iterate on a problem. So SkyMind is a company that basically helps you navigate your, the problems with deep learning, as well as the applications thereof, and if you should use it, and if so, how. So that also comes down to building these production services. So Alibaba actually mentioned before, distributed, so they have their image search, right, where they're indexing tens of millions of images. And based on this automatic content recognition, which I'll get into here in a little bit. And it took them probably, they have a lot of engineering resources. They have a lot of time to do this properly. Most companies don't have the know-how. And most of all, they don't necessarily know how to do it. So it's intractable for most solutions. So SkyMind is basically the industry-oriented approach to deep learning. So in this case, that's what the for enterprise part is. So one thing I often like to do with my audience is get an idea of who I'm speaking to. So first of all, you guys blew me away in the last presentation. I didn't know you guys were actually as technical. So I'd actually like to give you a round of applause for that. That's amazing. So I actually can give you a little bit neater content. That being said, I'm still going to ask who's here, so I know how to tailor the presentation properly. So am I speaking to any data scientists in the room? Software engineers? All right. That is what I was looking for. OK, so now I know how to tailor the presentation. So deep learning 4J actually, I'm sorry. What about just business intelligence analysts? OK, yeah. So mixed bag as usual. That being said, mostly software engineers. That is exactly who I target. Software engineers are the people who put stuff into production. They're the ones on the front lines dealing with, oh, this page didn't pop up properly. Oh, this machine learning algorithm isn't training on time. What do I do about that? So deep learning 4J is a way of bridging the gap between software engineering, production systems, and deep learning. So what exactly is a deep learning neural network? As mentioned before, there are several different kinds of neural nets out there. And what I'm actually going to do is actually summarize all of them at the end, their applications and what they're good for, and why, as well as visually represent each one. So we're going to start with the canonical representation of a neural net, the typical feed-forward neural network. So in this case, a neural network at its core has neurons that are meant to be a mathematical approximation of the brain. So if you think about it, when I touch this desk, I have feeling, right? So when I have feeling, a neuron fired, and somewhere along the lines, my brain basically gave me the sensation of feeling. We can approximate this with math. So in this case, you have an activation of an individual neuron. So in this case, what are neural nets good for? Recognizing patterns. So when I touch a desk, that gave me the pattern recognition of feeling. So this is obviously at scale with lots of data. This is huge, because all of a sudden we can actually turn lots of data, unlabeled data, into value. So again what was mentioned before, being able to do at scale feature extraction. So how many of you are familiar with the basic tenets of machine learning? Maybe I need to go into a little bit of depth. Okay, That's good because that means I can kind of explain and make sure that you guys learn something today. So in this case, when we, just a little detour, when we say features or images or anything like that, we have this idea of a feature vector. A feature vector is basically a list of numbers that represent some concept. So if we have an image is represented by pixels. The numbers 0 to 255 with the red, green, and blue channels. That can actually be represented as just one long string of numbers. So that's a feature vector. In this case, we have pixels, and those pixels get turned into a vector that can then be leveraged by a machine learning algorithm to identify patterns as well as classify them. So that's actually what's going on when you have a machine learning algorithm trying to learn something. So in this case, deep learning takes these features and tries to extract value out of them, some sort of trends. So the basics with neural nets is neurons fire on certain features being present. Those neurons get translated into higher level patterns that we can then use to extract value from data. So the audience for deep learning. So as I'd mentioned before, a very research-oriented topic was all of a sudden good for businesses, chief information officers, data scientists, and for those of you in the audience, software engineering. So software engineering are the ones deploying the production systems and leveraging these systems for whatever business problems they're trying to solve. So in this case, deep learning is, unlike what most people would think, is being employed by bigger companies. But the problem is, most people just don't know how to tune them, they don't know how to train them, and they can't iterate because it takes way too long to train. That's not good for a business. No one wants that. And on top of that, a lot of these other machine learning solutions out there tend to be closed source. You can't deploy them behind your firewall, only work for toy problems, and make lots of assumptions. Your company, I don't care who you are, is special. You all have your own needs. You all have your own problems. And most of all, you actually have different combinations of data that need to be analyzed. So visual search is a great example of that. So Alibaba, for their e-commerce products, including clothing, analyze and trying to extract clothing from images. That's a form of feature extraction. So they take that subset of that feature vector and say, this part of the image are clothes. So that's a business problem being solved. Chief information officers, though, they do not want that data going out the door. They have compliance concerns to be concerned about. They have all sorts of security. They monitor the infrastructure. They keep the ship running. So that's not tractable. And on top of that, why most CIOs want open source is because they want to be able to modify the code. They want to be able to do things with it. They want to understand what's going on. So in this case, my goal is to solve all of those needs. So not only being able to take what's in these crazy academic papers, implementing these algorithms, giving you a platform to do it on, and changing neural net timing from days to minutes. Companies have all sorts of hardware, but the hardware doesn't necessarily have all the necessary components, including GPUs, to train them. Deep Learning 4J actually solves that problem. So for any other deep learning framework out there, they might work in all sorts of ways, but they don't necessarily monitor reality. They don't actually reflect reality. So in this case, business-oriented deep learning, being able to solve problems for businesses, analyzing lots of unstructured data. So one thing I want to be clear here about, unstructured data is anything that you can put in a file. It could be an MP3, your music. It could be your images on your Facebook. It could be your reviews on Yelp. It could be, or whatever platform you use. Keep in mind, I'm sorry, I'm America. I'm American-centric. I'm learning things as I go here. That being said, some of you may use Twitter. So Twitter is another, it's like sentiment analysis. People are doing all sorts of crazy analysis with that. They're trying to do stock prediction, whatever. That's all unstructured data. Typically, and this is what's generated by people. People and data are synonymous. data is just our representation, like the representation of us online. Deep learning is a scalable way of actually analyzing those trends and being able to do trend prediction. And then, in turn, being able to solve business problems. So, who's using deep learning? These may look familiar. So these are the companies with deep learning teams. So I either have users from these companies, or I've talked to their research labs. You know, many of them have the dedicated infrastructure, but all of them are solving the same problem. So a lot of people are doing image search. Deep learning is way better for more than just image search. They're typically only solving one or two problems. So, for example, Microsoft Research, I was talking to them at a recent panel where I was at. And one thing that the guy mentioned to me was possibly doing a lot of text analysis with Microsoft. That's great. Yahoo, primarily doing images right now. Baidu, Andrew Ng was actually Andrew Ng was very, very bullish about doing voice. So he was actually pushing voice search as a way of, of you searching on your phone. So me being able to say, I want bananas, and then it brings up bananas on your mobile app. So being able to augment shopping or any sort of general purpose search. So images. So everybody's doing images with deep learning. It's what everybody understands. That being said, it's not the only one. Netflix, in 2007, they put out $1 million to anybody who could improve their recommender engine. Deep learning won that competition all the way back in 2007. Unfortunately, though, they didn't have the hardware to execute on it. Processors were too slow back then. Now, deep learning is tractable because we have the infrastructure. Companies have lots of data, computers are faster now, and we have a little bit more know-how about how things work. So in this case, that's what makes it tractable now. IBM Watson. So I don't know if you guys saw the Jeopardy challenge, where the Jeopardy World Champion. So Jeopardy is a quiz show game where all you do is the host gives you a hint, and you're supposed to respond with the answer. So basically, a robot actually beat humans in being able to basically take clues, assemble them, and identify an answer. Deep learning was used there. Amazon and their products uses deep learning for some of their review stuff as well. So part of their what products that you might like, you might also like, the recommender stuff. Deep learning actually generates some of the signals from this. Facebook, their research lab actually beat human accuracy in facial recognition, and they did this with the before mentioned convolutional neural networks. So again, certain neural nets are used for certain problems. So if you're curious about the event there, there's actually two challenges you should look at: DeepMind or DeepFace, and ImageNet. So ImageNet also beat human accuracy this year. Before that, computer vision was a mess. Computer vision, you had all sorts of crazy features that you had to generate. So again, those features are just distortions of an image, such that you can extract some sort of targeted signal from the image. So if you think about Photoshop or any of these image manipulation software, that's all actually feature extraction on images. We actually use the same stuff in Photoshop to extract value from data, from images, being able to recognize what a shirt is, building something called an edge detector that says, this is the outline of a shirt, and then basically giving that to a machine learning algorithm that can then identify those shirts. Yahoo. So Yahoo also launched a visual search algorithm as well. Google's DeepMind actually basically created a video game player. So what they actually did was they actually ran it through a moving window of frames on a game, playing a game, and it learned how to optimally play a game. All right, so you guys have seen enough brand stuff. Let's keep going. So one thing I want to make clear with data, it's only going to get more prominent over the years, especially with sensors as well. So sensor data, Internet of Things, the real-time services that people were talking about before, online, offline shopping, all of that is going to generate more data in the years to come. And we need to be able to adapt to those trends. Okay, so here's just a few names, just to kind of close out that chapter. For those of you who don't know the names in deep learning, these are the major players and researchers currently. Good? Okay. Okay, and again, I'm in all these presentations, there's always big data will take over the world and all that other fun stuff. Here's just some neat quotes. The potential for data, and especially unstructured data in the next 10 years, is only going to increase. And unfortunately, right now, data scientists who are paid immense amounts of money, that's a lot, they spend a lot of time doing this. Companies are spending a lot of money to just do manual feature extraction. So being able to take signal out of images or what have you, and actually say, oh, if this line goes here, this will happen, or this indicates that. Manual feature extraction is not scalable. Unfortunately, that's what we do with unstructured data right now. It's even worse in text. So in this case, being able to that's the bottleneck right now with being able to capture value from unstructured data. Again, unstructured data is anything that's a file. Your MP3s, your music, your reviews, your tweets, your Facebook status updates, doesn't matter. All that unstructured data, somebody had to manually look at it and say, these things are common in these ways, and this represents negative sentiment, or what have you. So there's just a quick summary for those of you who like slides. One thing that's mentioned, so search and information retrieval, same thing. Information retrieval is like basically the higher level field that represents give me relevant information. Just to kind of make sure. Time series forecasting. So whenever you look at charts, that's time series data. Time series data is used in purchases over time, churn prediction, you name it. So let's show you something neat. How about machine dreaming? How about the ability to actually recognize what is the general representation of a face? So machine dreaming is basically this I kind of like this term because what it does is it says, what is the neural net? Like if I showed a piece of data, what is each neuron? Each of these is a neuron that actually represents a face. For those of you who are curious, this is actually a restrictive Boltzmann machine representation of faces. So I actually taught a restrictive Boltzmann machine on how to recognize faces. You actually use this to basically create feature extractors then. So so an RBM is just basically a feature extraction neural net, and you train it to recognize faces. I'll throw out some statistics terms for those of you who are obscenely advanced. Basically, the unsupervised pre-training part of Hinton's papers that you've heard about, where it just learns the stuff, is actually called contrasted divergence. So contrasted divergence basically learns a representation of the data. Basically what it does, contrasted divergence basically simulates this process of, let me start with a random guess, and then let me just keep looking back and forth until I draw it right. That's what it's doing. Back and forth, back and forth. And then eventually what you'll get is, you'll actually get neural net weights or neurons that learn how to reconstruct these faces. So it starts random and gray, and then over time gets better. So it creates these feature extractors. So the unsupervised pre-training, the hype, the at-scale feature extraction, all that stuff you're hearing about is basically teaching a neural net how to reconstruct something by repeatedly showing it different examples. So that's what happens when you pre-train a neural net. This is just an initialization step. This isn't even training a classifier. So for those of you who are familiar, this is the unsupervised learning component of deep learning. So deep learning actually has two components. It has unsupervised, which is the pre-training, and the supervised. So I don't know for those of you who saw the earlier visualization with the convolutional neural net, where they had labels at the top that actually represented basically the classifier. So basically, the neural net actually has the previous layers be the feature extractors. It learns higher and higher order level trends, and then you train a classifier. Typically, for those of you who want to Google search a term, logistic regression or softmax regression on these features, or this higher level representation represents this person. Notice I said this person. So keep in mind, deep face specifically recognizes individual people. Not, is a face there? You. It sees you. It knows you exist. So it knows who you individually are as a person. So this is at scale. This is millions of people being recognized all at once. It'll know who you are when you walk into the store. It can say hi to you. There's going to be a lot of potential here in the coming years when the industry at large uses this, not just having it locked up in all the research labs. Because right now, that's where all of it is. Only big companies with all these resources are able to do cool stuff like this. When in reality, the future is now. The problem is distribution, know-how. So just another one. So I don't know if you guys can see it or not, but basically this is an optical character recognition. So again, I trained a restricted Boltzmann machine to reconstruct numbers. And the reconstructed I basically took a reduced representation of what the neural net was thinking and plotted it. And you'll notice that so this is on just 0 through 9. You'll notice all the 0s, 2s, and 3s are grouped together. It actually recognized that by itself with just raw pixels. All I had to do was show it raw pixels, and it was actually able to automatically group those numbers. So just to kind of make sure that we get it there. So like there's 5 and 6 in the bottom left corner there. There's zeros at the top there, on the top left, et cetera. So the end of this data set is 60,000. This is actually only 2,500 images, just for brevity. But I could actually plot this whole thing. What's really cool is this representation can also be used with words. Words can actually be grouped by usage. This is completely agnostic to language. I don't know how many of you guys have seen natural language processing techniques like search and all that aren't very good at identifying Korean text. What's with that? Deep learning is actually, that's because of manual feature extractors. A lot of the scientists, unfortunately, are English. Deep learning solves this problem because it's actually able to generate features or representations based on the word's usage that automatically identify this was used with this. That's all it does. It just does pattern association, positive and negative. So you can do this with any form of unstructured data. You can also do this with audio signal as well. So if I just have an audio signal, let's just say I have a line, I go up, and then whatever. That was somebody speaking. So you can actually you can actually represent data like that as well. So you can group it just like that. So the key that I want to show here is this idea of representation learning. Representation learning is this idea of taking unstructured data and learning some representation such that it can be used in whatever problem I'm solving. So it's this automatic feature extraction. So this is what allows deep learning to scale to tens or hundreds of millions or billions of images. Or combinations of text and images. So what if I want to generate a description of images from text? A description of text from images. I showed an image, in this case, this would be a presentation. That's a description I could generate from just taking a picture of this room right now. Or if I took a picture of you guys in the inverse, it would be an audience. An audience would have several components to it. It would have a lot of people, so I could actually count the number of people in here. Tables, laptops. Some of you might be taking notes or surfing Facebook. I know I'm not that exciting. But that being said, there's several components that I could identify all at once. All right. So representation learning, at-scale feature extraction. So use cases. So in this case, search is by far my favorite application. I'm primarily linguistics and natural language processing by trade, and I actually got into deep learning about a year ago. So I'm going to mention search a lot here. One idea is this idea of document clustering. So document clustering is basically saying, if I have a bunch of news articles and I want to learn trends from them, what I'll do is I'll actually group it by, this is about finance, this is about tech. So what I can do is actually automatically group those things based on the content present. The other one, so I mentioned earlier, Watson, is question answering. So this idea of asking a question and actually having a concrete answer returned. No search queries, no guesses, a straight answer. So another one, customer relationship management data. I see a lot with this. So being able to identify what a person's asking about and then automatically be able to answer their question. So CRM data is very common. Being able to identify positive and negative behavior in customers. Churn prediction. So in this case, the churn prediction part of this that I want to focus on is extra signal extraction from data. So if I have a customer taking a bunch of photos of cat pictures, I'll know they like cats, and then I can use that in predicting whether my service is going to retain them or not. So again, I've also mentioned recommendation engines. I'll just kind of keep going here. Enterprise resource management, so factories, logistics, prediction, oil and gas. So oil and gas does a lot of computer vision. And of course, the natural big data thing we have. Data is cheaper over time, and I think the more we accumulate, the more we should be able to extract value from it. Deep learning sort of scales to that problem. So one thing I want to mention: neural nets are slow to train. That's typically why they use the cloud, if you're doing it right. So this is where all the data lives. This is where it should also be trained. So computationally intense, very slow unless distributed, or on GPUs. It depends on the problems you're solving. So one thing I want to mention, resource intensive. Bigger companies tend to have lots of resources. But there hasn't been any framework up to this point that's allowed us to actually use all those resources. So one neat graph I want to show you is this is traditional machine learning accuracy. The more data you show deep learning, the better it does. So you'll notice it keeps going. That's huge. That's because of the representation learning I was mentioning earlier. All right. So I'm going to do a quick detour here and actually show you guys something a little more complex, just so you guys can kind of, I want to show you guys some actual good visualizations. So this was the hierarchical feature representations that were mentioned earlier. But raw pixels, one neural net learns edges, the next one learns parts, and then finally you learn individual people's faces. So this is all hierarchical representation learning. These are convolutional neural networks. So convolutional neural networks, the basic idea is you actually have a very small view of the world. You have something called a feature map. That feature map is literally just my eye moving around the room. So when you hear about position invariant features, that's actually what it's doing, is it's actually identifying like different parts of a room, and it looks at just a subset of the image. So again, low dimensionality, fast to train, if you have GPUs. So these are more computationally intensive, but don't require as much RAM. So faces, let me see. So for those of you who haven't seen this before, this is actually gradient descent. So gradient descent is basically what learns how to reconstruct the data or to learn a classifier. So this is pattern recognition. So what you'll see, basically what this is prediction error over time, and you'll see the more it iterates, the more it goes down. Your goal is to get to the bottom of that hill. So representation learning. Okay, this is a visualization of a restricted Boltzmann machine. So remember, I mentioned earlier, this is a feature extractor neural net. Basically, remember what I showed you where it does this, where it just like learns how to reconstruct the data by just looking at it over and over again? So that hidden representation were those faces I showed you earlier. So that hidden representation is the reconstruction. You have the visible that's then that basically learns from the data. So that's it looking at the data. The hidden is it guessing the data. And then what you have is the shared weights in the middle. The shared weights in the middle are basically what gets smacked around until it makes sense. So the weights that you see here, the lines, those are basically the neurons in this case. So an RBM is just a two-layer neural net. So a deep belief network is literally a stacked representation of that. So it's just an RBM followed by more RBMs, and then you have logistic regression on the end. So that's what learns how to classify images. So it learns higher and higher level representations, and then you have something on the end, logistic regression typically, that classifies the images. So this is just an example of, so a deep belief network can also be used for automatic grouping of data and basically compression of data. So this is on the Reuters data set. This is actually it being able to automatically understand, based on the content of the document, what the topic is. So deep leaf networks can be used for learning representations of data, as well as for classification. This is an augmentation of the image search that was mentioned earlier. So the one on the left is the query image, and then basically so if you have the image search engine that was mentioned earlier, what you'll see is that if you show it this flower, it'll actually bring back those flowers. This is completely unsupervised. So you can actually train a neural net to recognize content. Pumpkins will bring back pumpkins. And it will bring back the closest pumpkin possible, and also the color. So, okay. So this is another thing I want to mention. This is a recursive neural tensor network. So for those of you who are wondering, what do you do with text or images or hierarchies? What you can actually do is actually break up a neural net into a tree. So neural nets actually can be trees as well. So basically with text, in this case, the leaves are just individual word vector nodes. So if you remember those grouping representations I mentioned earlier, you actually have the bottom, you replace those bottom images with word vectors. So the word vectors are basically this word in vector space, the usage of the word. You can also decompose an image into something very similar, though. And then what you'll get at the top is basically each node has a label. And then that's actually how you do automatic scene parsing across the whole room. So this is with text, for those of you who want to just kind of see like how the texture representation looks. Either way, it's a tree. You learn a hierarchy of features. So text and images, both the same thing. So this is just so if you guys remember the visualization earlier, the visualization earlier was numbers. This is faces. Same thing. All right, and with that, I'll just kind of deliver a closing statement here. Basically, deep learning, great for unstructured data. Media has a lot of hidden meaning that can't necessarily be interpreted by humans. This gives us a scalable way and a slightly easier way to do that. So hopefully in the next few years, we'll bridge the gap. We have the hardware now, and now the goal is just to distribute know-how. Deep learning. Thank you.
예, 발표 잘 들었습니다. 질문 있으신 분 질문 하시겠어요? Okay. Adam, I have a question.
Yeah.
Well, about 20 or 15 years ago, there were buzzwords, machine learning, kind of similar to the deep learning. So, well, I'm not sure whether you are familiar to those technologies in that year, but what are the most important differences between machine learning in the older years and the current present ones?
So in this case, one thing I didn't mention, I also teach a basic machine learning component at actually a data science bootcamp in San Francisco. So I actually teach random forest, logistic regression, support vector machines, feature extraction, all the basics, data pipelines, data visualization. I train it all in Python. So I write Java and do big data, but I also teach all the basic algorithms. And what I will say to that is that when I mentioned the at-scale feature extraction earlier, the difference between machine learning and deep learning is this ability to scale with the amount of data you throw at it and avoiding the manual feature extraction part. So in this case, deep learning, you do vectorization and you analyze unstructured data. Machine learning is great for human interpretable results. So one problem with deep learning is this ability to actually take signals from fraud detection, for example, and identify when someone has a fraudulent transaction, what were the components of that and what were the triggers. So random forest is a great way of actually doing feature introspection on that and saying to your boss, because of the fact that this person on this date purchased 5 things within 10 seconds, this happened, or this was a fraudulent transaction. So the difference, to summarize, is manual versus not. Deep learning especially specifically focuses on unstructured data, or is at least best for that, because of the non-interpretable representation of data relative to the data being classified or patterns extracted from. Thank you.
Okay. So in principle, there are not that much difference.
No, so deep learning is a subfield of machine learning with a focus on neural networks. So I just kind of wanted to clarify that, like, the higher level details, like, this is where machine learning is used, this is where deep learning is used. This is the difference, and that's the difference between the two.
Okay, thanks. 다른 질문 있으신 분?
Hi, thank you for your great lecture. Actually, I'm not an engineer, I'm a business guy, so I think I understood half of your lecture. Sorry about that. As a businessman, we always, every day we face business problems and we have to solve them as soon as possible. You already gave us some great examples of how to solve the problems in our real world by your technology. So my question is that, can you give me some more examples to solve the business problems like we have to identify the segment of our customers and how to minimize the cost of the delivery, something like that. So,
right.
I mean, from my perspective, the deep learning is like a crystal ball that gives magical answers.
Right.
If I give you a bunch of the data.
Right. So in this case, deep learning, like I said, is great for unstructured data. So in this case, when I mentioned magical answers, I'm talking about the at-scale feature extraction, right? So this ability to say, these pixels map to this person. So that's great for signal in unstructured data. Other than that, you would typically use other machine learning algorithms for more basic problems like churn prediction and the like. So this is when you have unstructured data and you need to be able to generalize, generalize against text. Like, I don't want to have to do a bunch of manual feature extraction on text. I don't want to have to be able to say, if I modify the sound signal this way, this will happen. Or let me distort this image in 10 different ways and then solve 10 different problems. So the idea here is that you have something that's able to analyze data and understand the basic features of it. You would then use that as a component of a real production machine learning system. But it's not an end-all be-all solution. At the beginning of this talk, I specifically dissed deep learning for that exact reason. So I want to be clear, unstructured data, at-scale feature extraction, and focusing on business and focusing on it as a part of a production system. You still need to do vectorization. You still need to do a lot of the basic data cleaning and all that. This is just a part of the data science process. Focus on the unsupervised learning and the structured representation.
Thank you.
질문 또 있으세요? 저쪽에 마이크 좀 갖다 주겠어요? 네, 질문 한국어로 하셔도 동시 통역 가능하니까는 궁금한 거 있으시면 질문해 주시면 좋겠습니다.
네, 강연 잘 들었습니다. 한 가지가 여러 가지 데이터에 맞는 그 딥러닝 스트럭처가 다 다양할 텐데 그것에 맞는 스트럭처나 이런 것들을 기본적으로 세팅을 어떻게 해야 되는지, 뭐 레이어 구조라든지 이런 것들을 기본적으로 어떻게 접근할 수 있는지, 그 문제에 맞는 스트럭처를 어떻게 설계하는지 그것에 대한 노하우를 좀 공유해 주셨으면 좋겠습니다.
Sure. Okay. I'm sorry. Could you repeat the first part of your question? My apologies.
처음 질문 앞부분 한 번만 더 말씀해 주실래요?
죄송합니다. 딥러닝으로 풀어야 되는 다양한 문제들이 있는데 그 문제에 맞는 그 딥러닝 구조를 구조가 다 다양할 것이라고 생각이 됩니다. 그런데 기본적으로 문제에 적합한 그 딥러닝 구조를 처음에 어떻게 설계를 할 수 있는지 그 노하우나 이런 것들이 있으시면 공유가 좀 됐으면 좋겠습니다.
Sure. So the key here is that you do it visually. So in this case, one thing that has been developed somewhat is the ability to actually histogram changes in the neural net weights as well as other parts of the neural nets over time. So those visualizations I was showing you, where it was like you have the reconstructions of the faces, that's actually a debugging component. So you can actually see how well it's learning the faces over time. In this case, the other part of that question then is, what neural net do I use for what? So for an example, so convolutional neural nets, primarily used for images. Recursive neural tensor networks, typically used for images and text. And then the other one is deep belief networks and feed-forward neural networks in general. Great for most problems, depending on how you vectorize it. The other part of that question then is hyperparameter tuning. So what can I do with like momentum and Adagrad and all that? Like, so all those, so that comes down to tuning the hyperparameters. So the problem there, you actually visually debug and tune the hyperparameters, and then the other part of that is then identifying what neural net for what problems. If that makes sense.
Okay, thanks.